Last time we talked about timing attacks, and now it is time to talk about power analysis. But before moving on, let's recall our example and remember what the timing attack was. So our example was follows. So we are talking about physical attacks. Assume that you found a USB stick with a secret data on it. To access it, you need to enter an 8-digit PIN. Device has a delay response, so one trial takes 1 second. So there are 10 to the 8 different pins that you can enter. So in the worst case scenario, you have to try all of the keys, which will take 3 years. So what can we do? That was our question. And we said that since we cannot break the algorithm itself, we are going to break the implementation. So first we assume that it is implemented in a naive way. So assume that password check is implemented on an embedded ARM processor in a straightforward way. It checks correctness of the first digit. If it is correct, then it checks the second digit, and so on. So if your first digit is wrong, then the number of operations are small. But if it is the correct, then it checks for the second digit, and so on. So the execution time is directly proportional to the number of correct pin digits. So a timing attack can work like this. Select a random pin value, fix all digits except the first one, measure the timing for all 10 possible values of the first digit. The value that leads to the longest execution time is the correct one, because this means that your first digit pin is correct, and then the second digit is checked, which will take a longer time. So this way, set the first digit to this value and proceed with the next digits in the same way. In this case, at most you have to try 10 times 8, which is 80 trials. It will be enough to access the USB stick. So as I mentioned, you can perform the same attack on physical padlocks, and it works almost all the time. So if the timing measurement is noisy, averaging over multiple measurements needs to be done. In practice, this is not hard. But now assume that there's a countermeasure for the timing attack. So checking every digit of the entered pin is not a solution, because code requires more operations to be performed when a digit is correct. Assume that the designer of the USB stick inserts no operation instructions to balance the timing of both execution paths. So it doesn't matter if the password, the pin you entered is correct or wrong. It will take same amount of time for the device. So this way you cannot perform a timing attack. So our question was, how can we attack such a fixed system? So we will look, in this case, the power consumption. So the vast majority of digital circuits are implementing using CMOS logic. The instantaneous power consumption of devices implemented in CMOS depends on the instruction that is executed, the data that is being processed. So this way, if you put no operation instruction, then it wouldn't consume power. But when it performs a real instruction, it will consume power. So consequences for the pin check implementation: an attacker who measures the power consumption can easily detect whether no operation instructions are executed or not. So we can perform the previous attack, but this time, instead of looking at the time, we are going to look at the power consumption. So again, here we are assuming that we have physical access to the device so that we can measure the power it consumes. Select the pin value, fix all digits except the first one, measure the power consumption for all 10 possible values of the first digit. The value that leads to a significantly different power consumption than the other 9 is the correct one. Set the first digit to this value and proceed with the next digits in the same way. Again, at most you have to perform 10 times 8, that is equivalent to 80 power measurements. So this would be 80 measurements would be enough to access the USB stick. If the power measurement is noisy, averaging over multiple measurements needs to be done. So how can we now counteract the power analysis attack? So what can be the countermeasures? Counteracting power analysis attacks is a challenging task. Many publications are available on this topic. Assume that the designer of the USB stick is able to balance the timing and power consumption of both execution paths. So regardless of if the entered pin is correct or not, you would have an implementation which would consume same amount of power. That is the idea. And depending on of course, the algorithm, there are ways to do it, especially in cryptographic algorithms, for instance, in block ciphers. SBox operations are table lookup, so they would easily be recognized because they will consume more power. So there are ways to partition an SBox into smaller SBoxes, or you can turn it into logical operations like XOR, AND, or NOT, and so on. So this way, there are many ways, but of course, this is a challenging task, and there are many publications available on this topic. But assume that we somehow have a countermeasure for power analysis. So what can we do next? So this time we will talk about fault attacks. Digital circuits require certain operating conditions to work properly. So temperature range, operating frequency, supply voltage, etc. Should be optimal for the digital circuit to work correctly. So for this reason, now we can somehow modify these properties, like the temperature, operating frequency, and so on, and somehow insert fault into the system. So this will be called fault attacks. By changing the operating conditions, an attacker can bring the digital circuits into states with undefined or unpredictable behavior. So that is the idea. Of course, it is a large topic and we don't have much time to discuss, but idea is that you inject a fault into system, and by looking at the result of this modification, you try to get the information. Timing attacks are in particular relevant for asymmetric cryptography. For instance, when you're trying to capture RSA keys, you can look at the time, because depending on whether a key bit is 0 or 1, the number of operations you perform changes. So by looking at the time, if it is large, then you will say that that key bit is 1. If it is small, you will say that it is 0, and so on. However, attacks on symmetric cryptography is possible if either the software implementation is not done carefully and the hardware adds data-dependent behavior. Each intermediate data values of all cryptographic algorithm carries information about the key. So that is the main idea behind these attacks, actually. So let's see an AES example. During the matrix multiplication by 2 means shift left. If most significant bit was 1, before the shift, add this hexadecimal value to the result. So you might think that why multiplication by 2 is such a strange operation here, because this is not an integer multiplication, it is a field multiplication, because the multiplication is not, as it is written here, is not an integer multiplication, but it is a Galois field multiplication. So as you can see, there's data-dependent behavior even in AES matrix multiplication. So by looking at this, you can obtain that the most significant bit was 1 or not before the shift. Okay, because if it is 1, you perform an extra operation, so it will take more time, and also it will consume more power. So this is still an active topic, and but it requires some specialty, and it requires some hardware to perform these attacks. You need oscillators and so on to physically perform measurements on the device.